To go further now, we will have to introduce the concept of energy. I kept already saying many times that there is available potential energy in these stratifications that are set up, and there are ways in which the potential energy that's locked up can be released. And when potential energy is released, what happens? You get kinetic energy, right? So let's say you're holding something up in the air like this and you let go. Its potential energy is going to be released into the kinetic energy of falling to earth. So we will look at energetics of the thermal wind in this sense by defining the simplest of energy concepts again, which you have seen somewhere in high school physics already. The potential energy in the simplest way when you have elevated mass is Gz times the parcel mass of the parcel. So it's Gz times rho, the density of the parcel, times dv, the velocity. We are looking at parcel in the concept of these infinitesimal things we do when we want to derive equations, right? So PE, in this case, the potential energy of this parcel is, of course, integrating, or the air column is, of course, integrating over some height times rho dv. So we're just going to integrate this equation from some height to another height to look at the relative change in potential energy in that system. We can easily define mass as rho dv, integral of rho dv. Why are we doing integral? Because it's a continuously stratified system, and when you look at a certain volume, you have to integrate over that volume because it's not a constant density, right? So to define the center of mass, we can just go g times the mass as defined here times some height of that center of mass of that volume for which we are doing potential energy. Okay, very simple. So g, acceleration of gravity, times the mass of the volume we are looking at, and it's the height of its center of mass represented with this brackets. Okay, how is that height center of mass defined? Obviously it's the distribution of mass over that volume divided by the mass itself. So it's just integral of z rho dv divided by the mass. Again, it's because the rho has a profile, it's not a constant. Okay, we have to keep carrying that because we are looking at stratified bodies of fluid like the atmosphere and the ocean. Here is where things begin to get a little bit more interesting. We need the concept of available potential energy. Available means it's just sitting there. If you perturb it in some way, can that stored energy be released? Just as I said, if you hold something up and drop it, you're releasing the energy, right? So before, what we did was to deal with this in a concept of convection, where we were taking a stratified fluid with a stable vertical profile in Z, and we were displacing parcels within this fluid. We were taking rho 1 up to Z2 and bringing rho 2 down to Z1. We were just adjusting in the vertical, and we were looking to see how convection was happening. Is there a release of potential energy in this case? It was an incompressible fluid that we considered, and density is conserved during the displacement if it's incompressible. But if it's compressible, then even adiabatic displacements will release energy by condensation or evaporation. If it's incompressible, it's not doing any work against the environment as the pressure changes with height, for example, right? So you are not doing any energy, you are just changing the potential energy. So if you look at such a stable stratification, there is potential energy, but is it available? Right? That's the key question. We have looked at this profile several times, and we have said cold heavy air is at the surface, and there is warm light air at the surface, and yet it's not just mixing up. If you had a tank and you created such a situation by trying to have cold air, cold water, for example, incompressible, and warm water, you would just slush it and then you would mix it up, right? So we will see what we mean by that. So in a stable stratification, there is potential energy, but it's not available. If you do these adiabatic displacements, you're still going to maintain large-scale stable stratification, which means potential energy is adjusted, but it's not available to be released into kinetic energy. Okay? We are doing it in a kind of heuristic argument, but we will soon see the special situations where this stratification energy can be actually released, that how the potential energy that's locked up there can be released. Okay, so remembering our expression, potential energy is gravitational constant acceleration times the mass times the height of the center of mass. Adiabatic rearrangements of the air column has non-zero potential energy. Okay, it is locking up, it has non-zero potential energy, which means you are keeping air parcels away from their zero potential energy state by using rotation, but it's not available for conversion to kinetic energy unless, if it's stably stratified and everywhere it's just stably stratified, then you can do adiabatic displacements and nothing will happen. You cannot release that energy and create kinetic energy. But if you have horizontal density gradients, then you can begin to imagine that there is available potential energy that can be released. So, stable stratification requires non-zero horizontal gradients of density for P to be converted. It's not very complicated. So we have stable gradients in low latitudes, stable gradients at high latitudes. So locally they are stable, but there is a density gradient. That's what is critical for releasing that potential energy. That's a lot of words, but make sure you read the book, you understand the concept that I'm trying to describe. If I didn't do a good job of describing it, we will add more details as we go along. But obviously we have horizontal gradients and thermal winds based on those and so on, which means there is available potential energy because of these horizontal gradients, even though locally there are stable gradients.